To turn the projector back on. I have homework tests back in the office. Yeah. Bless. Okay. Section 1.3. Next time we'll be covering section 1.4. Then I think we're going to keep the review where it is and test, and then we'll do section 2.1 so that we don't we push back the history and math test so it wouldn't be on the same day as analysis. And then if we push this one back a day, then they'll both be back on the same day. So.
Question about history and math.
Mm-hmm.
Is the homework chapter 10 due today?
No, Wednesday. Yeah. Yeah, that one had a little bit much for everybody to get finished that day. But you should at this point be able to do the history and math homework because we went over the proof in class today that you have on the homework. So you should be able to start working on it.
Need two.
You did 2 of them already from history and math? For chapter 10 or chapter 9? Yeah, they're not bad, are they? Okay. Just in case there are any.
Only that really.
They really aren't bad.
Don't believe me, believe.
Okay. Look at these sequences right here. The section 1.3 is all about adding, subtracting, multiplying, and dividing sequences. So let's add, subtract, multiply, and divide. What is an plus bn? If I want to write a formula for this, if I know an is 1 over n, this is my an, and this is my bn. What would an plus bn be? 4 over n. You're just adding them together. What would an minus bn be? Negative. Negative 2 over n. What would an times bn be? 3 over n squared. And an divided by bn. 1 over n divided by 3 over n. Yeah, 1/3. A constant sequence. We like that, Clyde. Okay, now let's find the limit of each of these. That's what the next thing down is going to tell us. So what is this limit for this first sequence? 0. Notice the limit for each of these up here is 0. So this is equal to the sum of the limits. The same thing for this one. And 3 over n squared, 0, which is 0 times 0. And then 3.
And the 5. Is 0 divided by 0 or something?
Why
You have to do a limit to figure it out. So in other words, 0 over 0. Suppose this was your sequence 1 over n, and down here you have 1 over n squared. That goes to 0. That goes to 0. But if you simplify that, you'd have an n squared over n, which is n, which goes to infinity.
Why did you multiply it by next one?
Well, I'm just saying, yeah, I'm simplifying the fraction 1 over n times n squared over 1. Yeah, and that gives you n, which goes to infinity. So this one right here before you even go to take the limit, you actually have to simplify it. So this limit would actually be 1/3. But notice that we can't say that's equal to the limit 0 over 0 because that's undefined. So because the original limit was 0 over 0, we don't know what that is, we can't apply the theorem. The theorem only works when your limit is 1, 0. Okay, so that's a refresher from calculus. Yeah, we're going to prove them this month there. We are. Find the limit of each of these sequences. They did this after their theorems. You have an n cubed minus 100 n squared plus n minus 58 in the numerator, n cubed plus 65n plus 69 in the denominator. In calculus, what would you have done to find this limit? L'Hopital's rule or long division, you can do either way. If we do L'Hopital's rule, yeah, notice this goes to infinity, this goes to infinity. So by L'Hopital's rule, you're going to have 3n squared minus 200n plus 1 over 6n squared plus 65. Do L'Hopital's again. You get 6n minus 200 over 12n. And do L'Hopital's again because they both go to infinity. Or you can divide by the highest power of n in your denominator. So you'd have n cubed over n cubed minus, I'm going to run into myself over here. Let me put it above. You can have n cubed over n cubed minus 100 n squared over n cubed plus n over n cubed minus 58 over n cubed divided by, in the denominator you have 2n cubed over n cubed plus 65n over n cubed plus 69 over n cubed. Yeah, the n cubes become 1 and everything else goes to 0. So the numerator you get a 1 out of, and in the denominator you're going to have a 2 and everything else goes to 0. You can do it either way. You're going to have, I believe you have a few of these on your homework, like 3 or 4 of them, find the limits. You can do them either way, L'Hopital's rule or long division,
It's
or
like
divide by
finding
highest power.
asymptotes.
Exactly, that's exactly what it is. So look at the second one now. It's not a fraction.
You change it to power.
Yeah, that's exactly what we have to do. Well, except I'm going to actually find it as a product of something. This is a square root of n plus 1. That goes to infinity. This goes to infinity. Infinity minus infinity, guys. Yeah, we don't know.
Oh.
So we actually have to find a different way of solving this. Tell me what this is equal to. Yeah, they're different, so you can't cancel them. Square root n plus 1 times square root of n plus 1, what would that be equal to? N plus 1 minus the middle values and plus the middle values. Yeah. So
You can multiply by the conjugate if it's not like a
I'm
fraction.
going to make it into a fraction.
Oh, okay.
That's exactly where I'm headed. If I solve this for, this becomes 1 over square root of n plus 1 minus plus the square root of n, right? Then what should I do? Now we're looking for finding that limit. Well, I could multiply to get the conjugate, but I'm actually not going to do that because I then get a difference of square roots in the numerator again. What would this be less than or equal to? This is bigger than n. Yeah. And now where does that go? As n goes to an infinity, yeah. So this whole thing, that limit is actually equal to 0. Yeah, it was 0, but you never can tell when.
Yeah. But think of this way, n plus 1 square root it should be always bigger than square root n.
Yeah, it should be. But how much bigger is the question?
It's one.
It's one bigger.
So when you're taking limits of stuff, you can just change it to an inequality so that it will avoid something.
Okay, remember the squeeze theorem. So I know that 0 is less than or equal to that. Like Cly was saying, it's positive. And I know the limit goes to 0 from above. So I have 0 is less than or equal to the limit as n goes to infinity. So apply squeeze theorem, which we haven't proved yet. But we're just doing limits, we're not proving them. So apply the squeeze theorem says the limit goes to 0.
No, I thought it squeezed.
Because, yeah, squeeze between two zeros. Mhm.
I just came up with that.
Yep.
I thought it was because you guys made
No. They do, but no, this one is because it's kind of picture it, squished between two values that are the same.
Well, you could.
That's great.
It makes sense.
Okay, any other questions on that?
That's all our homework on?
Oh, no. This is analysis. We have to have proofs.
You could go one to
No, we can't. Okay, so here is our theorem. You'll recognize this theorem as pretty much the entire section with the exception of the last two theorems. If AN converges to A and BN converges to B, then AN plus or minus BN converges to A plus or minus B. AN times BN converges to A times B. And AN divided by BN converges to A over B when B is not equal to 0. We want to prove each of these. So we're going to have a proof that's going to kind of go sideways. The hypothesis, let AN converge to A, and our sequence BN converge to B. Now we want to show convergence, so we have to fix an epsilon. Yep, fix epsilon greater than 0. Apply your definition of convergence. That's the only thing we know for A and B right now. So there exists an N1 in the naturals such that for all n greater than or equal to N1, you have AN minus A is less than. At this point, I'm proving this is for number 1. At this point, I'm just going to use an epsilon over 2. Why would I think I might need an epsilon over 2? Because I'm adding them together. Yeah, I want to get epsilon. And there exists an N2 in the naturals such that for all n greater than or equal to N2, we have Bn, let's try that over again, B sub n minus B is less than epsilon over 2. How do we choose n? Is it the smaller? Yeah, the maximum. Then, for all n greater than capital N, you know that an minus, well, I'll put it this way. N is greater than N1, and so an minus A is less than epsilon over 2. and n is greater than n2, which gives, yeah, bn minus b is less than epsilon over 2. Now combine it together. Thus, for all n greater than capital N, you're going to have an plus bn minus a plus b. What did they do at this point? Yeah, I'm actually going to bring this over here now. I have my full page now. So we're going to have an plus bn minus a plus b is less than or equal to an minus a plus bn minus b by the triangle inequality. But what is an minus a less than? Epsilon over 2 and epsilon over 2. So that's epsilon. Thus, an plus bn.
I think we did similar thing last week.
Yep, for Cauchy. Now, let's see if we can actually kill two birds with one proof. How much does it differ if we had a plus, if we had a minus here, an minus bn? So if you have an minus bn minus a minus b. So you still factor that out as an minus a, right? Minus, yep,
Yeah, but then when you do the triangle inequality,
it still becomes a plus.
exactly, because of
Yeah.
this absolute value.
Yep,
So that doesn't change
it doesn't change a thing. So I am going to go through and put this as plus or minus. And then that's, everything else is going to stay the same. Do you guys see that there is absolutely no difference other than that?
I'll reach.
Is the power of what? Yeah. So one is proved. Now, yeah, we're going to prove the multiplication. So this is the same hypothesis, except I'm going to start with the fixed epsilon greater than 0. And I'm going to get a different n1 and an n2 for this one. Let's go scroll down the page just a little bit and see what an bn minus ab. Remember, they did a trick in the book. They add and subtract something so that you can factor it. So it's going to be a and b.
But why did they choose that to add and subtract?
You just need to either have this term in common or that term in common, and then one or the other of those. So they could have just as easily done
So they
B
could've
and
done
A.
B and A,
Yeah, it doesn't matter.
but you have to have.
It has to have one capital letter, one lowercase letter, and they need to be different so that you can factor it out. And then they applied the triangle inequality. And then what do you have in common from this first set of absolute values? Yeah. And then you're left with bn minus b. And what do you have in common in the last? Yeah, so absolute value of b, an minus a. Now, we'd really like to make each of these terms here be less than epsilon over 2. That's our goal. Because then the whole thing would be less than epsilon. So this one over here would need to be less than epsilon over 2 times something. So we need to be able to bound that an. We need it smaller than some maximum value. What did we learn about convergent sequences and boundedness? It should be in section 1.1. Every convergent sequence is bounded. Yeah. So let's write this down. Since AN converges to A, there exists an M in the naturals or in the positive reals, it doesn't matter. M greater than 0, such that AN is less than or equal to M for all N in the naturals. Question?
I was just wondering what two sides like that.
You need to write it down?
Oh,
You have it? Okay. Oh, went too far. Okay, so this is going to give us then less than or equal to capital M, Bn minus B, plus absolute value of B, An minus A. So now we can go write down our capital N's. Since An converges to A, there exists an N1 in the naturals such that for all N greater than or equal to N1, we have An minus A is less than, we want epsilon over 2 times the absolute value of B, and I want to make sure that that's non-zero because B could be 0. And then that will give me an epsilon over 2 for the last one over here. Does that make sense? This is not the same constant that they used in the book. Don't worry about that. Since Bn converges to B, there exists an N2 such that for all N greater than or equal to N2, Bn minus B is going to be less than epsilon over 2 capital M. And I know that the capital M is bigger than 0. We chose it. We're going to let N be the max of N1 and N2. Then for all N greater than capital N, we can come down here and we have the B terms are going to be M epsilon over 2M, and the A terms are epsilon over 2 absolute value B plus 1, which is less than or equal to this right here is going to be less than 2, so we're going to have epsilon over 2 plus epsilon over 2, which is epsilon. The book chose a second epsilon. You don't have to, you can do it this way. There's nothing that says that both terms in your sequences have to be smaller than the same value. So you can have different functions of epsilon to be able to do that. So this works just fine. So thus An times Bn converges to A times B.
But where's that one?
Which one? Oh, why did I put a plus 1 right here? Because what happens if B is equal to 0? You're dividing by 0. You can't do that. So I add a positive value to it. That way, I know the absolute value of B is never negative, but I have to worry about if it's equal to 0. Yeah. So I'll never divide by 0 then. That makes sense? You guys starting to see the pattern here. You choose a capital N for the AN sequence. You choose another capital N for the BN sequence. And you choose the biggest of those two N's and do some arithmetic.
Why did you choose epsilon over 2 absolute value B? I understand why you added 1 to that, but why are you choosing epsilon over 2 absolute value B?
because I have this absolute value of B right here times the A in sequence.
Okay. Oh, so you
And I
just
want
divide
that one to
it.
cancel it. So if I divide it, then it cancels. B over 2B plus 1 is less than 1/2. Yeah. Okay, looks like we have to insert another page.
Why did we, we just have a absolute value of B over, and you can't put the absolute value of B plus one.
It, okay, so let me write that down here. So you have absolute value of B over 2B plus 1. Notice that that would be, if B is not equal to 0, that would be B over 2 absolute value of B. So those are canceling, you get 1/2. So this whole thing has to be less than or equal to 1/2 if B is not equal to 0. If B equals to 0, then you're going to have 0 over 2 times 0 plus 1, which is still smaller than 1/2. That's how. Yeah. Any other questions on that? Okay, then we prove the division one, right, guys?
Okay, just copy these.
So that I just recopied it so that we could see what we were doing.
So we always know that AN is going to be.
Yeah, they have to. Mhm. So let's fix another epsilon. I'm going to give myself a lot more room. Let's do our arithmetic first of all, so we can figure out what we need our sequences values to be in comparison to epsilon. So you have A sub n over B sub n minus A over B. Okay, two fractions subtracted. What should we do? Common denominator. So we have A sub n B minus B sub n A over B sub n B. Now, we can't factor anything in the numerator, so let's add and subtract something.
So we have to have a term for each.
Yeah, we need a term from each. And I think we can do A's and B's, the capital A, B. Let's see. So from the first one, I could factor out the B on. And from the last one, I can factor out the A on. And it gives me what I need. So that's going to be less than or equal to ANB minus AB plus AB minus B and A. All over the absolute value, B sub n B. Factor out the B from the first one, and then you have A sub n minus A. And on the second one, factor out the A. Yeah, I'm good. Can I write it as B sub n minus B? It doesn't matter. It's an absolute value.
That is what it is.
Yeah, it doesn't matter the order inside the absolute value. We can change it. Yeah, the minus sign will go away when you take the absolute value. Okay, so what we want to do, and I'm going to write this denominator as absolute value B sub n, absolute value of B. Now, if I simplify it, I have the absolute value of B, an minus A, over absolute value of B sub n, absolute value of B, plus absolute value of A, B sub n minus B, over B sub n, absolute value of B. On the first one, does anything cancel?
Leave the,
Yeah.
gone.
those are gone, and so you're going to have an a sub n minus a over absolute value of b sub n. Plus, on the second one, nothing really cancels, so you have to keep all of those terms. But I'm going to write it as absolute value of a over absolute value of b sub n, absolute value of b, times that b sub n minus b. So you can kind of see we need a bounding term for this b sub n right here. We've got this b sub n. It's in the denominator. That means I need something bigger than it. No, I need something smaller than it to keep my inequality going the right direction. You divide by smaller to make your value bigger. So I need something smaller than b sub n. Well, all the b sub n's have to be bigger than something. But if your sequence is bounded, then it has to have a lower bound, right? And so we're just going to take the absolute value of the smallest value of the sequence.
Which is,
Well, we're just going to call it. We don't know what it is. We'll give it a name. Oh. Okay. Since b is not equal to 0 and b sub n converges to b, I know that b sub n is bounded. I have to be careful because I need this bound to be something bigger than 0. I can't be 0. So the smallest value of this sequence might be 0. So I can't exactly choose the smallest value. But I can choose a value so that it's going to be bigger than 0. So I know there has to be an n1 in the natural such that for all n greater than or equal to n1, b sub n minus b has to be, well, I'm going to do it this way. B minus the absolute value of b over 2 is less than b sub n is less than b plus absolute value of b over 2. Remember the book used that b over 2? And it can choose that b over 2 because b minus the absolute value of b over 2 I needed an absolute value, so I'll just do it that way. I need the absolute value of b sub n. It has to be close to capital B. It has to be less than b over 2 away from capital B. Or I can make it b over 4 or b over 1,000,000. It just has to be close to b. So I know that it has to live in this neighborhood for some infinite amount of time. But what is capital B minus b over 2? Yeah. And that's for all n greater than capital N1. So then that takes care of those b sub n. So then this would be less than or equal to n minus a over b over 2 plus, and now we have a bn minus b, and the b sub n over here becomes absolute value of b over 2 times absolute value of b. I would submit to you that this number is a constant. Right? It's not changing. And this number over here is a constant. It's not changing. And b was not equal to 0. So if I want each of these to be less than epsilon over 2, what do I need the a sub n's to be? Maybe you want one more step in between. What do you do with that fraction that's in the denominator? What do you do when you divide by fractions? Flip it and multiply by it. Sometimes I don't get the question answered right. Question asked right. And this is a 2 over, 2 absolute value of a over b squared, bn minus b. And I want each of these less than epsilon over 2. So for the first one, that means we need epsilon over 2 times 2 over absolute value of b. Okay, so let's go back up there. Too far. Since an converges to a, there exists an n2 in the naturals, such that for all n greater than or equal to n2, we have an minus a is less than epsilon over 2 times, what was in front of that? I forgot already, and I didn't want to have to scroll back down. 2 over absolute value of b. And then the 2 over absolute values of b are going to cancel. Since bn converges to b, there exists, we're up to an n3. We have bn minus b is less than, let me move this fraction up a little bit. There. It's less than epsilon over, that one was downright ugly. We'd better go look at it. 2 over 2a over b squared. So that whole part in front is going to cancel. We're going to let n equal the max of n1, n2, and n3. Then for all n greater than or equal to capital N, we have, and now our proof is complete. Except for our conclusion. Thus, an over bn converges to a over b when b is not equal to 0. And now our 3 proofs are done. Did we like them? Not too bad. I would get to where I know them because these proofs we're going to see again in chapter 2. We're going to see them for continuous functions. They're going to be identical. It looks almost, remember the difference between a sequence and a function is a sequence is only defined on the natural numbers, and our function is going to be defined everywhere. But it's going to be the same kind of proof. Instead of there exists a capital N, we're going to use a delta, but that's the only difference. Everything else looks the same. All of our arithmetic is the same. You see this one, these ones again. So I would memorize them now. Okay, that was all of our theorems up to, we have 2 last theorems here. If an converges to a, bn converges to b, with an less than or equal to bn for all n, then a is less than or equal to b. This is not quite the squeeze theorem, but very close. Let's prove it. What's the hypothesis on this one? Okay. I have to show that a is less than or equal to b. going to prove that? Yeah, they use an epsilon on that. But remember, they approached this by proof by contradiction. So what would be the opposite of A less than or equal to B? Yeah.
That's greater than.
Yep. Suppose A is strictly bigger than B. Now this is where they define their epsilon to be equal to B minus A over 2. Halfway in between. So if this is your B, wait, A minus B over 2. Which one did I say was bigger? Yeah, A is bigger than B. So I need this to be A minus B. Epsilon has to be a positive value. So here's B, here's A. So here's the midpoint between the two of them. And so half that distance, there's a neighborhood of epsilon around each of them. They don't overlap. Okay? But I know that A minus epsilon is equal to B plus epsilon by construction. Now, I know that AN converges to A. So there exists an N in the naturals such that for all n greater than or equal to capital N, I know that AN minus A is less than epsilon, which says that minus epsilon is less than AN minus A is less than epsilon, or that A minus epsilon is less than AN is less than A plus epsilon. But tell me about this A minus epsilon. B plus epsilon. So that tells us that B minus epsilon, it'll catch up, there we go, it's less than B plus epsilon. That is equal to A minus epsilon is less than AN is less than A plus epsilon. Now, tell me about the B sub n terms. If Bn is converging to B, right? Don't need a so there. There exists an N2. I better call this N up here an N1. My ones and my commas look very much the same. Sorry about that, guys. Okay. There exists an N2 in the naturals such that for all n greater than or equal to N2, we have B of n minus capital B is less than epsilon, or B minus epsilon is less than B sub n is less than B plus epsilon. I'm going to choose n to be the maximum of these two. We're going to have B minus epsilon is less than B sub n. It's less than B plus epsilon, which is A minus epsilon, which is less than A sub n, which is less than A plus epsilon. That tells you that B sub n is less than A sub n. But what did we know in our hypothesis about B sub n and A sub n? Yeah, that's a contradiction. Thus, I know that B has to be less than or equal to A as desired. Any questions on that one? Like it, maybe, maybe not? I didn't say you guys would like proofs at this point. Yes, I hated proofs for the first year that I took them.
I don't know. I understand when you go to your class, but when I do homework,
It hurts.
I don't know.
Hmm.
I feel like I wasn't listening, but I was.
It's
Oh.
completely 100% normal at this point.
But I feel like I'm the only one.
I guess I feel.
Oh, everybody
more
feels like
so
the only
since
one.
I was gone for a year. And,
Trust me, you're not at any
Yeah.
more disadvantage than anybody else. Those of you who took set 3, okay, you just took it last
Just 4
summer. Does
months
it make a
ago.
difference? Nope.
It's just 4 months ago.
Yeah,
You teach them
for
theory
set theory
No.
and logic in the summer?
Devin was changed to major, and so he was going to have to wait an entire year after he finished all his other classes or take set 3 during the summer. So took it during the summer.
You offered set theory in the summer?
Nope, only directed study, and only in very special circumstances.
I was like, yikes. Set theory in the summer. Oh,
Yeah.
gosh. What would be even worse is intermediate
That was
analysis
so
in the
much
summer.
work.
Done that too. In a month in the summer too, mind you.
What?
Yeah,
Jesus,
Oh
how
my.
I only do it, I offer, when I do directed studies, I do them for the month of May to the first week of June, usually. So you have 4 weeks. I guess it's the second week now in June because we have graduation second Sunday, but yeah,
like a test every week.
pretty
I
much.
might have to stay close to your house or something.
Yeah, it's- And
And
I only meet with students once a week. So you work on it, you watch all my videos multiple times, attempt it all, and then we spend 2 to 3 hours once a week working on homework. Okay, it's not fun. I don't recommend it. It's not fun for me either, trust me. If AN converges to 0 and BN is bounded, then AN times BN converges to 0. This one actually looks relatively short in the book. It's not a very long proof. Yay. What's the hypothesis? Yeah. And let AN converge to 0. And BN be bounded. Well, BN is bounded, so what does that mean?
Is that absolute value of the
Yeah,
is less than some.
it's some number. I'm going to choose it in the natural so I know it's positive and bigger than 0. Yeah, that's capital N. I'll give it a little tail. There exists an M of the naturals such that for all n in the naturals, B sub n is less than or equal to capital N. Okay, let's do our algebra. We are going to have AN, BN minus, except we don't have a limit, but we're multiplying this bounded value, this sequence, by 0. What happens when you multiply something? 0. Because we're trying to show it converges to 0. Well, what is, when you subtract 0, what does that give you? Well, now let's take absolute value of each of them. But what are the B sub n smaller than?
And
But now I can subtract the 0 on the A sub n. And I would like somehow to make that smaller than epsilon. So what do we need to make this a sub n minus 0 smaller than? Over m. Since a sub n converges to a, there exists an n in the naturals such that for all n greater than capital N, you have a n minus, it converges to 0. I'm so used to a. A n minus 0 is less than epsilon over capital M. I know capital M is bigger than 0 because it's in the natural, so I don't have to worry about division by 0 here. This is going to be epsilon over capital M times capital M, which is going to be equal to epsilon. So what's our conclusion? An times bn converges to 0. Yeah. Fascinating. That is all there is for section 1.3, addition, subtraction, multiplication, division of sequences. Your homework from section 1.3 is applications of these theorems. Make sure that you read over the hints. They're going to give you hints in a couple of problems. Make sure you read over those hints. Okay, we are done with that. If you have questions on the homework that is due today, you can go ahead and ask me. Let me save this really quickly first. And stop this.